Like you just said, my name's Randy Zwitch. I work at OmniSci. We used to be called MapD up until, I think, 2 or 3 weeks ago. As it turns out, there was a lot of confusion about what our name meant relative to what our product does. And so rather than have to keep introducing that, we just switched our name. So what does OmniSci actually do? OmniSci is a GPU-accelerated relational database and analytics platform. And what's really great about GPUs is the massive parallelism works really well with the type of workloads that are generally done on relational databases. And so if you're doing something like a group by statement or a filtering statement, a where clause, GPUs actually work really well for this use case because of the massive bandwidth that GPUs can stream data through, as well as the massive parallelism that you get with the GPU core. Before I go any further, do I actually need to explain what a GPU is, or is everybody comfortable with that? I didn't want to insult everyone's intelligence to start off with, but I'm happy to go over it if anyone would like me to.
Okay. Could you just maybe speak for a minute about the architecture of GPU?
Sure. So the way I like to explain the difference between a CPU and a GPU would be something like a school bus versus a Ferrari. If you want to get somewhere really, really quickly, and especially if you want to go in a straight line or a racetrack, a Ferrari is fantastic. And in this case, in my analogy, the Ferrari is a CPU. So CPU's clock speeds go really fast. They're general purpose in some natures, but ultimately you can do one thing really fast. Okay? GPU, on the other hand, is the school bus in this analogy. So GPUs, in terms of clock speed, are much, much slower. But if you want to get 50 people down the street, it turns out that the GPU, or your school bus in this example, is the better way to do it. It may move slower, but you move more through. Okay, so you move more people down the street. And so GPUs, for the longest time, were used to render graphics on a computer. But in roughly 2007 or 2008, some enterprising researchers realized that graphics, your regular image, is really just a two-dimensional matrix of values. And they said, well, hey, a lot of scientific computing and machine learning are two-dimensional arrays of numbers as well. And so they realized, for what ended up becoming CUDA, the acceleration library, that you could do relatively the same thing. And so, again, what makes GPUs really great for analytics is that you're going to essentially do the same operation to different data elements all at the same time. So if I want to square 1,000,000 elements, I don't need to do them one at a time. I can do, say, 5,000 at a time, or however many GPU cores that you have. And if you contrast that to a CPU, it may be able to do that operation faster, but you end up doing those operations serially, and it takes longer overall. Okay? And so OmniSci was built from the ground up to work with GPUs. And so while OmniSci may not be as flexible a tool as something like Postgres, for the operations that we are optimized for, we are extremely, extremely fast. And so what I'm going to do today is present OmniSci just briefly, because I don't want this to be a vendor talk. I don't want this only to be a vendor talk. I want to actually show all the work that is going on as part of something that's called the GPU Open Analytics Initiative, of which OmniSci is part of. Okay. Before I go too much further, I don't want to forget this. We just raised a bunch of money, and we need to hire a lot of people. So if any of you are C++ engineers, CUDA engineers specifically, like giving talks and would like to be on my team, we are hiring lots and lots of people. We are a remote-friendly company, so that pitch is out there. If anything you see here today interests you, please come talk to me afterwards. And of course, if the product interests you as well, please come talk to me. So what I want to do is demonstrate an end-to-end workflow where the data stays on the GPU throughout the whole time. And the data source that I'm going to be demonstrating is electricity demand on the eastern part of the United States. And so where OmniSci fits in for the GPU Open Analytics Initiative is we're a great storage and computation medium to start off with your data exploration. Okay. So as I said before about our name confusion, just as a tangent, almost every one of our demos has a map of some sort in it, and that's where the confusion came in. So everyone thought we were only mapping software, but as it turns out, the relational database capabilities are a much stronger piece of our product offering than the maps. But nevertheless, we have a map here that outlines the region for the electricity demand that we're going to evaluate. And so I just have a simple dashboard here showing our data set for electricity demand over maybe a 10-year period or so. And there's plenty of tools that can display data like this. But where OmniSci becomes interesting is that everything that's on here is being rendered by the GPU instead of having the data being transferred from the GPU to locally on the CPU and then rendered with JavaScript. And why is that important? Well, for the data set that I'm using here, which is relatively modest in size, it's not a big deal. But if you want to have drill down capability of anywhere in the United States for hundreds of thousands, millions, billions of data points, you can't stream that across the browser. You need to either downsample your data or just not visualize it at all, which has been the sort of current state of affairs. And what GPU rendering allows for is that we can get record level granularity while also having interactivity. And so this map here again highlights the region of interest that we're going to talk about. But if we want to start looking at our data, we have this heat map here, and we can use this for cross-filtering. We can drill into any portion of our data at any time. And the easiest way to sort of see this is by using this cross-filtering tool at the bottom here. And so as I go through, this is all going in real time. There's no caching going on. In fact, OmniSci doesn't support indexing at all. GPUs, from sort of a brute force perspective, can stream the data through so fast that it actually slows us down to have indexing. And so as you can see, we can just go through this data point here, and we can slide through. And all of this is being sent back. All of these tiles submit a query to the database sends the data back. And so we can start to get a level of interactivity that you're not going to get from a lot of other tools. And so from what this data actually means perspective, so as we scroll over this, this chart at the bottom here, as you'd expect, electricity demand is very cyclical. Anything that has a human behavior involved tends to be very cyclical. So, times where people are awake, obviously people are going to use more electricity than when they're sleeping. When it's hotter outside, air conditioning tends to drive up electricity usage. And then you start to see, with the electricity demand chart over here, an interesting perspective of you get these dips. And so how people consume electricity tends to differ between the summer months and the winter months. And so every time you see this bimodal chart pattern, these tend to be our winter months. And again, we can go over this, through any time period. We can scroll around. Okay, so this is the gist of what the OmniSci platform does. We provide a reporting platform that's GPU accelerated, but we also have a raw database editor where you can type in SQL and things of that nature. Yeah.
That answers the question. There's two different schemas. Engineering and visualization labs as required consulting you, or can it be done using the query?
I'm sorry, could you repeat the question?
You know, yeah, I suppose I give you a different database with a different schema, and I want to visualize different things. So that requires engineering, and that is delegated to you. So that's you know, if something the customer needs to ask the company, or it's something that can be engineered using SQL editor.
Oh no, all of this can be done by the end user. It doesn't require coming to us. In fact, the core OmniSci engine is actually open source, so you don't have to ever talk to us if you don't want to. If you want to use this visualization interface, this is part of our enterprise product. But ultimately, I wasn't planning on spending too much time on this, but we have, like many different database engines, you could just import your data through our browser if you have a small enough data set. We provide Python, JavaScript bindings, if you want to do your work that way, a command line interface. We accept streams from Kafka, any number of tools. And so, no, you don't have to ever talk to us.
Good question. Who's hosting the GPUs? Are you hosting the GPUs, or you have them on the cloud?
Okay, so for this example, I'm using a Microsoft Azure instance. This is just a coincidence. It doesn't happen to be that because we're Microsoft. Our product works on any of the major cloud providers. It works if you have your own GPUs in a data center. We also have a product called OmniSci Cloud, which is a software as a service platform. That's where we actually have our own platform where we're hosting GPUs and deal with all of the maintenance. But ultimately, any way you want to run this, you can.
Any minimum requirements for the GPUs?
In terms of minimum requirements, we get the most speed up if you can have your data in GPU RAM. And so when I'm at home, I use consumer grade GPUs. If you're going to do this in an enterprise setting, you'll want to use data center quality GPUs. But you can scale both horizontally and vertically. And so for the most part, 8 GPUs tends to be the most that you can get into one node without doing weird things. OmniSci, as I said, is both horizontal scaling and vertical scaling. So we do support distributed node GPU clusters as well. Okay, so this is where we're going to start with. So all of our data can be stored in MapD. And so now I want to actually get into the part that moves the ball forward. So using our library, which is still called PyMapD, that will eventually change. We're going to import data from OmniSci into Python. But what we're going to do here is through interprocess communication, we're not going to transfer the data anywhere from the GPU. What we're going to do at really low level terms is OmniSci returns a pointer to the data, and then PyMapD reads that pointer, and it leaves the data in the same location. And this is where you end up getting a very interesting workflow, is that through the power of Apache Arrow, it's possible that multiple different tools can pass references to the same data set in the same memory location, never serializing the data. And that's really the biggest issue, not the biggest, but a painful issue in data science when you have to transfer data from one system to another. And how do you do that? Whether, you're passing CSV files around, or maybe you're using Hadoop and you have Parquet files and you're trying to pass this from here to there. And this data serialization in and out of tools wastes a great majority of time. And so what GoAI, the GPU Open Analytics Initiative, along with Apache Arrow is really trying to solve for is by using a common in-memory format, you can avoid all of this copying and passing data around. Okay, so to do this, some relatively normal. Is this big enough? Should I make this bigger, or can people see this?
Bigger.
Bigger. All right. Okay, and so this is relatively standard code. I'm going to be importing pandas, PyMapD. And when we do our connection, we can see the data that we had in OmniSci is now displayed on the screen in the Jupyter notebook. And so this table is fairly simple in its construction. We have two timestamps, the difference just being UTC versus local. The region, and then MW stands for megawatts, the amount of energy demand. Okay, so if we want to pull a data sample, again, we'll use PyMapD to do so. And I've started doing some basic data cleaning here. It really just depends on how much performance you really need, where you do this data cleaning. In this case, I'm a very big SQL person, as opposed to what I see as sort of dichotomy. If you generally a pandas person or you're a SQL person, you generally don't see both. So I'm a very big SQL person. Of course, I work at a database company. That makes sense. So I'm doing some really basic feature engineering here, taking the characteristics of a timestamp and moving them into separate columns. And so as we do this, okay, I've just taken a small sample of data out of the database. But again, we're not passing it across CPU or not streaming it to the browser. This is just a reference into GPU memory. Okay, and so now we have a very simple, like I said, a very simple set of features. As it turns out, forecasting electricity is actually a really simple problem in time series because people behave so statically. People go to work at 8, 9 in the morning, come home at 5 o'clock, they turn on their air conditioning, they go to sleep 10, 11, whenever people go to bed. So even though the features are actually very simple for this model, it fits very well without needing to use any crazy predictive modeling techniques. And so now that we have our data inside of a GPU data frame, I'm just going to demonstrate using CuPy. So this is the CUDA version of NumPy, how we can do just a simple linear regression and predict energy demand very, very well. And so the first thing that I want to do is one-hot encoding. So if you're familiar with scikit-learn, this actually has the same semantics as scikit-learn. So getting all of this acceleration is somewhat free if you're already in the Python data ecosystem. Free being sort of a relative term because GPUs are expensive. But if you already possess GPUs, you don't need a lot of specialized knowledge to do something like this. And so to build my model, I'm going to use day of week, month, and then hour of the day, which we saw in the dashboard to be pretty good in terms of being able to show decent separation in how people consume electricity. And so when we do this, okay, again, if you've done this in scikit-learn before, it should look exactly the same. We've created all of these different 1-0 flags for the different combinations of day, hour, and month. And just because this can be a little confusing about where we are, I just want to highlight this again. Okay, I'm using the pandas pretty printing interface to show it here, but the data is actually on the GPU, and so just wanted to point this out here because if you're watching this here, I'm sure it's probably pretty tough of when are you transferring memory or when you're not. But ultimately, I've not transferred any data off the GPU at this point. It's all references. Okay. So now, like any other predictive modeling project, I'm just going to split the data into a training and validation set. And again, to really just keep reinforcing this, data's still on the GPU. Nothing's changed. Again, we're just creating references. Okay. And so now we can get to the point where we start doing something that looks like NumPy. And so what I'm doing here is just splitting my data into the independent variables and then the thing that I want to predict, which energy demand. And now we've gone from a GPU data frame to GPU arrays like you would see in NumPy, except rather than using NumPy and doing a transfer from GPU to CPU, we leave everything on the GPU and just CuPy generates CUDA kernels in the background. Okay. So now if we want to calculate the model parameters, we can do this a dozen different ways. Generally, you wouldn't see anyone do it this way, but I'm only going to demonstrate it because it's an interesting application of, or interesting intersection of linear algebra and GPU processing. So I'm going to solve this directly. Usually, you'd probably see someone do something like gradient descent to estimate the model parameters. I'm going to use the normal equation to actually generate this in one fell swoop. And so you can see we have, it takes 497 microseconds to go through and do the dot product of our X matrix, invert it, go through and estimate all of our model parameters. And so this is one of those areas where GPUs really shine. As you're going through and trying to do matrix multiplication, again, all of those cells are going to be independent of one another, which means that can be a highly parallelized problem. And in the case of the GPUs that I'm using, I believe the total cluster has something like 24,000 CUDA cores. I believe this is only running on one core, so you're still getting 5,000 threads at a time that's solving this problem. And again, linear regression isn't a very difficult problem computationally, especially when you do something like gradient descent. But again, I've taken the worst way to solve this, and it still can be done in 500 microseconds. And so now we can go through and actually try and evaluate this model. And again, I'm doing all of this in sort of the linear algebra way of multiplying through like you'd see in NumPy. But again, using CuPy, you're getting the GPU acceleration essentially for free, because the API of CuPy does its best to mimic NumPy. So if you're already familiar with one, you're generally going to be familiar with the other. And so then we can go through and calculate some simple statistics of root mean square error, and then we can do mean absolute percentage error too. And so you can see with just this simple example, we've not transferred the data off of the GPU. With just a simple handful of features, our average error is 9.2%. And so if we want to go through and visualize this, this is an area actually cheating. And so depending on how you look at this, I am going to transfer the data to CPU to do visualization. This is a small enough data set where it doesn't matter. There's several different ways you could do this. I didn't want to make this a really vendor-heavy sort of situation, import the data back into OmniSci, build a dashboard. So I'm going to just use the matplotlib functionality. And so this area is the cheating part. If you notice here, the pd.dataframe. So I've now transferred the data off the GPU to the CPU, and now we can go through and visualize our model. And so you can see with just this simple set of features and really elementary linear algebra techniques, you get a pretty good fit, okay? You'll see that for the most part, this data set, here, let me zoom this. Okay, make it a little easier to see. For the most part, our model does fit human behavior here with just a handful of dummy variables. And so in the areas where the model doesn't fit, sort of gets into the more domain knowledge situation where certainly weather affects how people use electricity. I don't have weather as part of this data set, but if I were to add that, you would see the delta here shrink dramatically. Another area would be economic activity. So depending on the area that you're looking in, if it's a booming area, electricity usage goes up because there's more factories, more commerce. If you have an area that's not doing so well, you'll see electricity demand go down. But again, Almost all of this, other than the visualization here, has been done on the GPU with no data transfer, no need to serialize data. And so what's sort of the future of this? This is a stylized example, of course. It's a small enough data set that I really could have done this locally in a CPU. But the point of this is that great strides have been made towards solving one of the worst problems, in my opinion, in data engineering and data science, which is, again, the serializing of data between one place and another. There's something, if I click on here just to get the logo list, there's something like a dozen companies that have bought into the GPU Open Analytics Initiative at this point. Anaconda is one of the big sponsors through the NumFOCUS CUDA compiler, or I guess just GPU in general. It does both AMD. There's Graph Analytics, H2O is a machine learning platform, and then through, if you're a GPU person, you've been following along, NVIDIA just announced last week, I believe, that they've sort of rebranded the GPU Open Analytics Initiative into something called Rapids, which is essentially the tools that makes all this work. So all the low-level C libraries, various things. And so the future of this is, we hope more tools will start to buy into this shared memory platform. I know, or at least at one point I think, pandas was being rewritten to use this same memory format. NVIDIA claims there'll be visualization libraries coming soon, so I won't have to do the cheat that I just did of coming to Matplotlib. OmniSci already does render the graphics on the GPU, but it's pretty low level. If you're familiar with Vega, the D3 grammar, or Altair. So Altair is what? Altair is written in Vega Lite, which is a grammar of Vega, and Vega is a grammar of D3. So this is all coming close to fruition. There are a couple of rough edges where one object doesn't quite talk to another. These are all really low-level things. They're not going to be solved by the average end user. But ultimately, there are a lot of really talented people working on this, not only at our company, but again at NVIDIA and all of our partner companies. And so the future, I think, of being able to use GPUs for analytics end-to-end is really bright. If you're interested in how to get started with this, these are all intended to be open source initiatives, and so all of the code is hosted on GitHub, not just from the OmniSci perspective, but the GPU data frame and all the surrounding libraries are also open source. And on that, I'll open it up to questions. That's all I was going to present. Yeah.
So you mentioned a lot of the Arrow transferring pointers data.
Mm-hmm.
So that basically implies to me at least that it has to be immutable. You can, because you don't want one process to modify the data that referenced by a pointer, and that proliferates into excessive memory usage. So what attempts are made to free memory, and how is that managed?
So generally, I'm going to put the caveat out there that I'm not one of the engineers that's working on this, but within the various tools, you generally see when the handoff occurs, they take possession of the pointer. And so you're not copying the memory around using the same reference, but eventually one of the tools takes possession of it.
So there is a garbage collection, or
To be that's more specific, unfortunately, than I can answer. But yeah, the idea here is generally that one process is going to hand it off to another and then take possession of that memory location.
So Bison hands over through, say, Arrow memory to Spark, and then Spark can free that memory?
I don't know how Spark, I don't know the Spark internals, but yeah. So if you look in our library, we use, OmniSci uses thrift to pass our messages. And so one of our messages is actually to free the memory from OmniSci. And so how each of these tools sort of works through this will be seen, you know. I don't know the internals of all that, but yeah, essentially you're passing the reference, you're not making a copy. Yeah.
So I can see how it'd be nice to have all of the data science tools talking to each other without having to copy memory. But I'm wondering, from a database perspective, where you might have multiple users making queries on this database, do you see an issue with having one user then keeping something that they're interacting with on the memory of the same GPU that the database might be trying to use?
Yes, and so the one thing to keep in mind, and this is really just specifically for OmniSci, is that we tend to view ourselves as an analytics platform rather than a transactional database. And so, yes, if one user is doing all of their work on the GPU, then you could have an out-of-memory situation. But the expectation would be that an analytics team would sort of manage that themselves. Because again, this isn't really for transactions or a production system where data is going to be streaming in and it has to be readily available. It's more of a exploration tool. Yeah.
How has, like, if you have like a much larger data set that isn't like fitting on like memory on the GPU, how is like the scaling been on that? So like is the like acceleration outweighing that communication overhead? And sort of like where's that like tipping point?
Sure. So one thing that we do specifically is we save our data in our own. It's funny to say this as I'm talking about interoperability, but we save our data in our own proprietary binary format locally. And so we use not only GPU RAM, but CPU RAM as a cache. And so as people are using data in sort of the hot state, we try and keep it in the GPU RAM. If another data request comes in, that table may or may not, depending on how much memory is being used, kick out the original data and push it to CPU RAM. And then if nobody's using it, it just gets, we just go back to disk. So we're always storing the data on disk. But the thing about GPUs is the bandwidth is so high that us streaming the data from disk tends to be pretty quick as it is. If you're using NVMe drives and then multiple GPUs in parallel, you can get 6-10 terabyte a second bandwidth. And so it really depends on how large is large. I used to work at a very large media company, and you'd need lots and lots of GPUs. You'd have to do a distributed cluster. But for many applications, you really should be okay streaming the data set across. Even this data set here, okay, this one's 42 million data points rendered on a map, right? And you're getting full interactivity with this data set. You can zoom in to wherever you want to go. So this is all being loaded into RAM. We have demonstrations on our website of 1 billion or even 10 billion data points where you can get full interactivity. Yeah.
Do you support more than NVIDIA GPUs?
So we don't, only because NVIDIA is such a dominant player that it really doesn't even come up from any of our prospective customers or current customers. Yeah. Oh. So it looks like there's 5 more minutes. Go ahead.
Well, on the data side, the database side, how do you handle the geographic coordinates? What sorts of projections do you support? Do you explore that?
Sure. So we natively support points, lines, multi-line, polygon, multi-polygon. We support just a handful of projections. Geospatial is one of our newest functionalities. If this is something that interests you, I'd actually love to talk to you afterwards about this. We're really trying to understand the needs of the community. If you look at a tool like PostGIS, there's something like 1,000 operators. We're never going to implement all 1,000 of them, but we'd love to get 85, 90% of the normal use cases. Okay, well, if there's no other questions, thank you all for coming today. If you're interested in OmniSci, again, as a product, come up and talk to me. If you're interested in, especially if you're an engineer, come talk to me. If you want a sticker or a t-shirt, I have them. Otherwise, again, thank you all for coming. It was great to be here.